Hey everybody, Mr. Smith here. Welcome back. Before we dive into our topic on nuclear physics, what we're going to do is take a very quick tour through some of the basic discoveries that led us to be at the point where we are historically. And at the end of the deck, we're also going to give you a chance to work on some very basic skills that you probably already have. If you find out you don't have them and they're not basic to you, then raise a hand and make sure you speak up loud and clear early on so we can help you with them, okay? So to begin with, we talked about Benjamin Franklin, big upshot of this experiment. All matter contains just two types of charge. From there, we talked about the invention of the battery. Luigi Galvani and Alessandro Volta led the way to the creation of the enormous battery at the Royal Institute of London. And it's with the invention of the high voltage battery that a lot of new discoveries get unlocked, not just chemical elements like sodium and calcium and so on, but things like the electron itself. So J.J. Thomson's discovery that it doesn't matter what I make these metal pieces out of, the anode here and the cathode over here, I draw off with high voltage the same exact particles out of every metal. So in a way, it really puts an exclamation point on Benjamin Franklin's idea that there was something simple going on at the heart of all of matter. Then we get to William Rankin's discovery of X-rays. What was Rankin doing? He's using an apparatus that's actually very similar to what J.J. Thomson did, but what he does with the electrons is to stop them. So he generates electrons and slams on the brakes by colliding them into metal. What happens is he generates radiation, and the radiation can travel through matter. So eventually he gets to the point where he's got a tube right here, which is where the electrons are being stopped and the X-rays generated. The X-rays are then used to expose a photographic plate. What's he done though? He's put his friend's hand in the way. So what you know it now, and I'm sure you've experienced it yourself, is that X-rays stop in bone. They're not stopped by flesh. This experiment goes everywhere, and it's just a huge social breakthrough where science makes an enormous contribution to the well-being of people. But also, the high voltage idea, it continues. The photographic plate idea also continues. Henri Becquerel is a researcher in France experimenting with salts of uranium. What he wants to do is expose these rocks to sunlight because sunlight contains UV radiation. What happens when you do that? These rocks actually glow. So he was intending to capture images of these glowing rocks with photographic plates. Anyway, he has an enormous accidental discovery. He has a couple of bad cloudy days in a row. He puts the whole apparatus, the photographic plates wrapped in black paper, the rocks, everything, into a desk drawer and leaves them overnight. When he comes back, he finds out that the photographic plates were already exposed. You can see on this image right here an outline of a rock. You can see also the outline of another image below it where you have a rock here and a Maltese cross that he had underneath the rock. And what does it indicate is that there's something going on with some of these rocks that no one ever expected possible. So the rocks themselves are emitting radiation. That puzzle is pulled apart to a great extent by the work of the Curies. So Pierre Curie and his more famous wife Marie Curie isolate different chemical compounds inside of these uranium salts. The most radioactive they call radium. Another one they isolate and they name it after their home country of Poland. Ernest Rutherford takes our understanding of radioactive materials another step further. He puts radioactive material on the inside of this lead block and enables radiations to spew outward in a column. Then he bends those radiations using charged plates and finds out that there are two that he can identify. There's a particle he calls the alpha particle. It's positively charged, as you can see, and it bends a little bit as it goes through these charged plates. There's a beta particle that's charged negatively, as you can see here, and it bends a lot more. So what does that mean? Alpha particles are heavy. Third, there's another researcher in France who's a colleague of theirs, Paul Villard, who identifies the existence of a thing he calls the gamma ray. It has no charge, and it turns out to behave a lot like a high-energy X-ray. Okay? We're really getting into modern times for sure now. Of all the discoveries, probably the most important is this one right here, the discovery of the nuclear atom by Ernest Rutherford. What did he do? A very similar setup to the alpha, beta, gamma experiment. He has radioactive material inside here that's going to spew alpha particles. What he expected was that if he puts a gold foil sample right here and spits alpha particles at it, the particles will stop because gold is a solid. Even thin gold, like a gold leaf, is still a solid. And that's not at all what happens. There's two major surprises inside this experiment that you need to know about. The first is that almost all of the alpha particles stream through the gold foil as though nothing was there. So solid matter, mostly empty. The second thing that was earth-shattering was that every once in a while there was a rogue alpha particle that ricocheted back at some really high angle. What that indicated was that all of the positive charge inside of the atom had to be in an impossible place. Namely, all crowded together in a tiny, tiny thing that Rutherford called the nucleus. So here's an image of what the nucleus would look like. We know now that the nucleus occupies about a 10,000th of the volume of the atom. Absolutely minuscule. And this is the heart of a lot of the puzzles that we're going to peel back as we talk about the development of nuclear energy. So a couple last slides to go out. There's a student of Ernest Rutherford's, Henry Moseley, who's a fantastically talented researcher and who dies tragically in World War I, who discovers the periodic table really should be organized by protons, that it's protons that give elements their fundamental characteristic, not their mass. Finally, the Cavendish laboratory that Rutherford is in charge of unleashes in 1932 this just unbelievable outpouring of research. First of all, Ernest Rutherford discovers that he can force, by bombarding nitrogen atoms with alpha particles, to emit protons. So he is the first person to ever fundamentally attack the nucleus and change it. A member of his lab, Chadwick, discovers the neutron. That's a really crafty experiment we could talk about later. And finally, there's the last one we wanted to talk about. The Van de Graaff generators that we showed you pictures of early in the lab were used as the first atom smashers by guys like Cockcroft and Walton. And what they did was they used streams of protons and they disintegrated lithium, forming helium and energy. And really, the moment where the possibility of an atomic bomb begins to glimmer in people's minds goes back to this moment right here. So we've got all the components right there that you need to really understand the beginnings of nuclear chemistry. We've got protons determining the element. We call that the Z of the atom. We've got neutrons that have almost the same mass as a proton. The neutrons plus the protons equals the atomic mass of the elements. And then we have electrons surrounding the outside. And in neutral atoms, the number of electrons equals the number of protons. That's why they're uncharged. So first example of a basic thing you should be good at would look like this. We're going to do, to make sure everybody has the skills to do it, an example right now. And what I'd suggest is you pause the deck, write this down, and do it on your own, and then I'll give you the answers for it in just a second. So lithium-6 is an isotope of lithium. It's a version of lithium. It's going to have 3 protons, because from the periodic table I know that's what makes it lithium. We'll write the atomic symbol, and then I'll write the 6, because that's the mass. If I write lithium-7 is still lithium, so it has 3 protons, but it's going to have a mass of 7. What I can do with that now is just work my understanding of the periodic table. The number of protons is 3. That determines the element. That's the atomic number. The number of neutrons is the mass minus the number of protons, because a neutron has a mass that's almost the same as a proton. So lithium-6, 6 minus 3 equals 3, and 3 electrons to go against my 3 protons means this guy has no charge. So what's going to change with lithium-7? Almost nothing. Still 3 protons, still 3 electrons, but I do have a 4th neutron in there. And why that is the way it is, that's interesting, and we'll get to that. Before I do, let's go and write out this next one. Sodium is what Na stands for, and this is going to be sodium-23. So in sodium-23, what have I got? 11 protons. In most atoms, I'm going to have 11 electrons, so this is uncharged, so it's 11. And this one's going to have 23 minus 11, or 12, in the neutron department. And we're almost out of the woods. Now, with this one, we have to be a little smart, and we have to understand that if I have 12 protons, I can go backwards and look at my P table if I want to. And I see that 12 protons belongs to this element over here. So that's magnesium. So this is going to be magnesium, and the magnesium is going to be magnesium 26. How do I know that? Well, the mass is equal to the number of protons plus the number of neutrons, right? So the symbol is going to be pretty easy to write. It's 12 Mg and 26. And the only thing I have left there is just the number of electrons, okay? So we'll do a worksheet like that. Hopefully that seems very easy to you. If not, speak up. Finally, one more thing that I think is very basic is you'll notice if you ever look at a periodic table that the masses that they give you are not nice, even, round numbers like I just indicated they were. The mass of lithium in reality is 6.94 when I sample it out in the real world. So why is that? And the reason is that lithium comes in isotopes. So isotopes are just the same element, same number of protons, but a different number of neutrons. And I picked lithium because it's a really easy one to work with. If you go sampling lithium out in nature, there's only 2 isotopes of lithium that survive for any length of time. So these are the ones, if you dig a shovelful of lithium, you're going to get just lithium-6 and lithium-7. But the principle I'm going to show you works for all of the different elements in the world to explain how we get this number for beryllium is 9.012. How come it's not just 9? Well, here's what it is. The mass of a lithium-6 atom to a lot of significant digits is actually not just 6. It's actually 6.015122. The mass of lithium-7 is given this way. And what you do to determine the periodic table average, or the average mass per mole, is a weighted average. So what am I going to do? I'll take 7.59%, so 0.079, 0.0759, and I'm going to multiply that into the mass of the element or the isotope that it's modifying. So 6.015122. And to that, I'm going to add, same idea, 0.9241 times the mass of the lithium-7 isotope, 7.016004. So go ahead and do that, add them up, and you will get 6.94. Double check it, and I'll see you in class. So bring your questions. Talk to you soon. Take care. Thanks for watching. Bye-bye.